happening right now. Even though we're hearing a lot about LLMs, I think behind the scenes, there's a lot of stuff happening with molecule generation as well. So here's Ben.
Hey, thank you. So yeah, as always, this is a group discussion of this paper. So I'd welcome anyone just to stop me at any point during the presentation and add to the discussion, like whether there's a point that comes to mind or a question, or even if it's just an insight that you have that I may have missed from reading the paper yourself. So jump in at any time. So welcome. Yeah, this is the paper Zero Shot Molecular Generation via Similarity Kernels. And I'm really excited about this paper because I think it's a sign that points towards the success of diffusion models and certain parameterizations of neural networks in generating molecules and approximating potentials of atoms, of interatomic, so molecules, for all sorts of applications. And it's presented in a really nice way that could be applicable to different problems. And so this is a paper from some of the world's most experienced and accomplished researchers in the space of machine learning for interatomic potentials, which are the potential energies of molecules. And they are also working on the physics of molecules and machine learning in general for physics and chemistry, and using machine learning and their expert knowledge to bridge gaps in understanding and to overcome intractabilities in computation. So looking at the title, it's generating molecules via similarity between features, and the features are coming from a parameterization of a neural network that produces potentials that are physical. And so what is...
do you mean to be sharing your screen?
Yeah, I should share the screen now. Thanks for reminding me.
Can see it.
Cool. Yeah, so let's read the abstract just to give us an idea and bring us to the same page. So generative modeling aims to accelerate the discovery of novel chemicals by directly proposing structures with desirable properties. Recently, score-based diffusion generative models have significantly outperformed various approaches. And key to their success is a close relationship between the score and physical force, allowing for the use of powerful equivariant neural networks. However, the behavior of the learned score is not yet well understood. Here, we analyze the score by training an energy-based diffusion model for molecular generation. So I think there's a good reason to use energy-based models. And one of them is this parameterization using powerful equivariant neural networks. And the energy can be parameterized in a way that has the right physical equivariance. And what that means is it's going to be invariant to a group, which is a group that represents rotations and translations. So it's going to be invariant to translation, because if you translate a molecule in space, then the internal forces don't change because there's no external force field. And secondly, if you rotate the whole coordinate system, the internal forces should also rotate. So that's equivariance. Rotation is equivariant and translation invariant. Furthermore, it's kind of arbitrary what order that you use to represent the molecule on the computer. For example, the ordering of the atoms, right? Because they've got to be ordered by some index base. When you put the array of the input of the state, which represents the positions of the atoms and the atomic contents, like the elements. So that array has an order to it, and you've just assigned an index to each atom. But that's completely arbitrary. So if you to change the order of the atoms, the relative forces between the forces of each atom don't change. So it's also got 3 permutation invariants, and that's kind of baked in to this neural network via message passing. The translation invariance is baked into the neural network because the inputs are relative positions. So it's like the position of this atom minus the position of this atom. It gives you this vector. And if you translate the whole atom, this vector doesn't change. And the clever part is the equivariance with respect to rotation. If you rotate the coordinate system, then the internal forces also rotate. That is baked in with more complicated parameterization that is outlined in this paper in the section about the maths. So we'll go through that. So they find that during the generation of score, the score resembles a restorative potential initially and a quantum mechanical force at the end. So training a diffusion model to generate molecules, a diffusion model is going to start from the data distribution, add noise. So the terminal distribution is going to be pure noise. And denoising score matching is the approach when the limiting distribution is a Gaussian. So that pure noise distribution is a Gaussian distribution. And then it's possible to learn the score via an approach known as denoising score matching. So they're trying to study how this score is going to relate to atomic forces. And now they've said here that it relates to a quantum mechanical force at the end. So that's the only way in which it relates to atomic forces, because quantum mechanics is approximating the forces between atoms in the physical world. So if you're going to add noise and start to corrupt this molecule, then things are no longer physical. But they can be useful to guide the molecules towards areas of space, which you see in a data set. And so what that looks like is the restoring potential, because if you've got a noise, pure noise distribution at the limiting distribution, then this potential is going to be quadratic, and it's like simple harmonic motion. It's just going to find the equilibrium of that distribution, which restores it towards the origin somehow. So it's a restorative force. Initially, so that's at time t equals big T. But remember, in diffusion, we're going backwards in time because with noise now we're denoising. So restorative potential at t equals big T. And then we're going to take time backwards and go towards a more physical potential, which is closely related to this quantum mechanical force at the end at time t equals 0.
Sorry to interrupt. This quadratic potential, would that mean that the molecule sort of clumps together in that limit, or?
So what it looks like is molecules are not bonded to each other. It's a particle cloud, which is going to be around the origin with some mean 0.
So the atoms don't see each other anymore. Just
they don't see each other. Yeah. There is no correlation.
Thank you.
But in reality, in physically, if you've got a protein, then even this molecule, this atom over here, is going to be correlated to this atom over here. Now they might be correlated, but they're not going to be bonded because we don't have action at a distance. They're going to have local interactions, but the chain of local interactions ends up with a correlation. And so that's the idea of message passing, which is why message passing is a useful inductive bias to have in modeling potentials. Now, one of the key points of this paper is that the message passing is good because you can represent information in edges, and then you want to go one step across in the adjacency matrix and model like third order interactions. So not edges, which is a second order interaction between an atom and an atom, but third order interactions between three atoms. And if you were to write down some model of quantum mechanics, then the overall potential is the summation of second order interactions plus the potential from third order interactions plus the potential of fourth order interactions, and so on. But the problem is with a message passing neural network, if you were to model third order interactions, that's 2 layers of a message passing algorithm. Fourth order interactions, that's 3 layers. And once you've got this, then it becomes computationally expensive, and you're tying this order of interaction to the amount of layers in the network, which comes with its own problems. And so one of the really clever things about this paper is, and the previous papers that this is based on, is that they've come up with an efficient sparse representation of potential functions that capture third and fourth, fifth order, nth order body interactions between these atoms, and done that in a way that still scales in a constant with the molecule size. So it still just depends on summing those atoms and then forming what is known as a tensor product after the summation over atoms. And so because the summation is done, and this tensor product is not a tensor product over this neighborhood, then that part can still scale constantly with the size of the molecule, which in turn is going to allow them to generate molecules which are hundreds of heavy atoms. In the context of molecule generation, the score is closely related to atomic forces. Consider training data that comprises configurations sampled using molecular dynamics or other methods from an underlying Boltzmann distribution. This is a nice thing to explain. This is actually the physical link, Peter, between the potential, the energy, and the force, which is the gradient of this energy. So the Boltzmann distribution is some kind of physical distribution if this potential represents the physical energy. And so molecular dynamics will sample from this Boltzmann distribution, where X represents the state, and the state is the set that represents a molecule, and with R the atomic positions and Z the chemical elements. So Z could be like one hot vectors, an array of one hot vectors representing chemical elements and maybe their charge. This potential B is a temperature parameter. So if you are doing some molecular dynamics, then you would decrease the temperature over time, and that temperature also has like a physical analogy, which is putting the molecule in some kind of heat bath. So if the temperature is high, then you have high energy configurations. The molecules are jiggling around quite a lot, and if the temperature is low, then the molecule is quite stable. And it's like an exploitation trade-off. If your temperature is large, you're going to explore different states of the molecule because it's jiggling around quite a lot. But only when the temperature is low can you find a low energy, which means high probability. So you want likely configurations of the molecule, but a temperature that is large is going to explore different configurations more freely. So when the elements are fixed, the score of the distribution corresponds to the atomic force. which is the negative gradient of this potential function up to the constant, which is representative of the temperature. Okay, so then the significance is that the atomistic modeling community is built on an extensive body of knowledge, building excellent models of atomic forces in the form of force fields. And those forces, that knowledge can be used to build networks that would predict the forces between molecules and be used for molecular property prediction. However, starting from a random sort of uninteresting configuration of uncorrelated atoms in a soup, using a force-like quantity to move the atoms to generate physical structures doesn't work so well, apart from in very specific conditions like periodic materials under high pressure. But it's not suitable for generating large complex molecules, because once you sample from an uninteresting distribution and start minimizing a physical potential, you'll get to a place which is uninteresting but physical. So what you'll find are the probability density is concentrated on the most stable chemical compounds, which are simple molecules such as water, carbon dioxide, and dinitrogen. I don't know if I agree, and I'm not an expert at all, that the probability density is concentrated only on the stable compounds, because you would expect that any physical molecule, the probability density is concentrated there. It's just that it's initiated at a place where these atoms are far apart, and so they're going to cluster together into water and carbon dioxide, which is the closest physical position, the closest physical state to the initialization. And whilst it finds something physical immediately, which is high probability, it's not going to be that interesting. So the idea is to how do we guide the generation towards molecules of interest, which are larger molecules.
You could maybe sort of argue that these are also the energetically most stable things. So, right, when you let any large molecule sit for a long time, it eventually does decompose into those. So it's maybe because it's sort of annealed, or so that it just happens so fast that it actually does end up in the very most stable compounds. But then it's only the chemical composition that sort of prevents it from being anything else.
True, but I think that optimization in a high dimensional space is such a difficult problem that even if you have a perfect potential, the idea that you're finding a global minimum is quite far-fetched. So
yeah,
so like, even if this is a global minimum, is the thing is the pathology, is the thing that's going wrong the fact that we're finding a global minimum, or is the fact that's going wrong that we're finding a local minimum that's not interesting, and that local minimum happens to be some kind of global minimum which is really stable that you can't get out of?
yeah.
I think they mentioned that one of the downsides of this method is that when you're trying to come up with new molecules, it encourages fragmentation into these like really stable compounds. So maybe you're right that it's not a global minimum, but it might just be that like the landscape is very jagged when you come close to being able to produce these molecules from where you are at, and it just will go into a local minimum with these molecules.
Could there also be like an entropic effect? So normally one of the reasons why stuff decomposes is because these are all gases, right? And gases are entropically quite favorable because they can go anywhere. Now in this particular problem, as far as I understand it, the degrees of freedom that are associated with this movement are sort of not integrated out, but so you don't see them anymore. So the temperature doesn't really take effect of that. I wonder whether that whether there still might be some backdoor where this sort of effect might come in, that there are just so many more states that lead to these particular combinations than lead out of it. Yeah.
A further problem of using this for molecular generation is that moving atoms along atomic forces does not allow for change in composition. So this is, I think, a huge insight breakthrough that these models, you want a model that is reactive, or chemically reactive. And that's a model, think about what you need for that. Like, you can't have a fixed functional form of an energy, because if you did, then the size of the input, the dimensions of the input cannot change. So if you have a fixed functional form, then you need to set the number of atoms to be fixed. So you need to generate molecules of, say, 9 atoms, and you can't move out of that framework. But as soon as you define something that is reactive, that has no fixed functional form, that can take as input any number of atoms in any particular state, then you can start to generate molecules of varying size, which I think is an idea that can be used in generating all different types of graphs and not just molecules. Because the thing with this line of research is it's not modeling molecules as graphs. It's modeling the physics of a molecule. And so that when they have a visualization of the molecule after it's been generated, yeah, it has edges, which to me suggests an adjacency matrix, but in fact, there is no adjacency matrix. The edges are inferred by the atomic distance between the molecules. So here you've got one of the applications of this paper, which is taking fragments of a molecule and bridging the gap between 2 atoms. And so that it's going to take a concept set, guide molecular generation using the features from the parameterization of the neural network, as well as this interpolation between the restorative force and the quantum mechanical force, guiding them with the features that are learned from this diffusion model, and ending up with a configuration of any number of atoms in between bridging the gap. Okay, but the links are just a visualization. So there's no adjacency matrix. It's just if there's an atom within 5 atomic units of an atom, then there is a link between them. So it's quite flexible. You can model any size of molecule. But then how do we swap out between different types of atoms? Because those are categorical variables. So what they do is split this force into a physical force, which is dependent on, is the gradient of a potential with respect to the position of the atoms, plus an alchemical potential, alchemical force, which is the derivative of the full potential with respect to the chemical composition. Okay, so now moving on to how do we parameterize the neural network to approximate this potential here. So there's some rules, and in modeling physics, it's sufficient to model potentials accurately as long as the potentials are functions which belong to a certain class that have some symmetries. So symmetries such as translationally invariant, so if you're shifting the molecule, the internal forces don't change, and rotationally equivariant, which means if you rotate the coordinate system, the internal forces would also rotate. And on the other hand, this alchemical force should be both translationally and rotationally invariant. And what that just means is rotating the molecule will not change or affect a change in the chemical composition. So given these symmetry requirements, it's no surprise that most recent works have used equivariant graph neural networks to learn the score. And a number of works are referenced here. In particular, a good one to read is this, because it seems to be a particularly good paper to read for graph generation with diffusion, because it treats the continuous and discrete nature of the graphs quite well and quite generally. So why have they done something different to that paper then? Let's first discuss the merits of papers such as these. So, given the success of learning these quantum mechanical forces, they have some merits, and a key merit of this is the principle of message passing, wherein the representation of each node in the graph, which corresponds to an atom in the molecule, is updated based on the states of its neighboring nodes. So successive layers of the message passing encode increasingly higher body order information. So body order information means interaction between atoms. Second body order interaction, 2 atoms. Third body order interaction between 3 atoms. Fourth between 4 atoms. When building force fields, locality is typically imposed by only allowing atoms that are within a certain cutoff distance, a neighborhood of each other to communicate. And this allows scaling, so constant scaling in the molecule size, because the neighborhood remains fixed independent of the molecule size. And it also reflects a physical intuition that most interactions are short range. You don't have action at a distance. In contrast, all previous works, so this is the difference, what are they doing differently? In contrast, all previous work on generative modeling for molecules has employed the global models, which represent molecules as fully connected graphs. But this poses 2 challenges. Global models are inherently hard to scale, so they wouldn't scale with the size of the molecule. And the model can't exploit the inductive bias of locality, that we don't have action at a distance when learning the force like positional score.
Then, so does the paper that you just showed us as a good paper, does that also take into account locality, or treats the molecule as a complete graph?
I'm not sure.
Okay.
Let me have a look. I think I've got it right here. I'm pretty sure it would also use message passing. Let's have a look. Baseline model. You know what? It could be a global model actually. Because there's not much mention of message passing here, but I'd have to go and read the paper.
Yeah, I guess the intuition behind locality is something along the lines of like the magnitude of the force between molecules. Isn't it like divided? Isn't it divided by like the square of the distance? So as you get farther and farther away, it just gets much smaller. So that's why you only need to take into account local forces. Is that not true?
I'm not sure.
Yeah.
Yeah, like the inverse square law. Yeah, I think there's like a very simple model of the potential between atoms, which has van der Waals bond, and the van der Waals bond is quite accurate. The inverse square law for that is quite accurate. It's like an accurate model of how particles interact far away from each other. And so it's going to decay quite quickly as you go farther apart. So now they're going into the details of training score-based generative models, which are trained by applying a linear projection to the learned features. I think this is just referring to denoising score matching. But an alternative is to not train the score, but train the energy. And then the score is the derivative, the spatial derivative of the energy, similar to this Boltzmann distribution thing here. So the score is the derivative of the energy, the spatial derivative of the energy. This is more expensive because training using denoising score matching first requires you to have the score, which is a derivative through the network of the energy. So each training step requires backpropagation through a network. Okay, so it's expensive to train. But it comes with some advantages. It's interpretable. The integral of the score corresponds to a learned molecular potential energy and enables us to study the energy landscape. So that's what they're doing. They're now going to study the energy landscape and take away lessons from that. Why is the diffusion energy or diffusion force so good for pointing towards a data distribution for generating molecules which are large and not fragmented? The reason that is they find the surface is surprisingly smooth, and that makes sense. The diffusion model adds noise, and so by add noise, you convolve density with Gaussian. Convolving with Gaussian smooths over density, and it penalizes fragmentation. So they have some numerical experiment which shows this is the case.
So yeah, I might have completely missed that. The a chemical force is that is also diffused over, right? So how does it work on something that is, you know, supposedly integer? Does it do first some dequantization or something on it, and then?
Yeah, I don't think the details are actually explored in the paper here, but because they are binary random variables, then one thing you can do is define on a continuous line some interval in which the binary random variable is positive is 1, and on the not interval it's 0, and so underlying that is a continuous space.
Yeah. Cool, thank you.
And then you add noise on that continuous space. So maybe that's how they do it, and that's across like a one-hot vector basically, or representing the chemical composition. So with this insight that we can build larger molecules with diffusion models, they're going to propose a way to generate molecules without the need to train a specialized generative model at all. This is the zero-shot aspect of the paper, and it involves constructing a smooth potential over pre-trained descriptors of local atomic environments. And so they're going to use a pre-trained MACE. So this is the parameterization that they use, which is equivariant to this or invariant to this physical group, which produces physical potentials to define a score-based generative process. And since training this physical potential, and parameterize it in a way such that you can interpret the features as being local descriptors of atoms within a molecule, then the descriptors are locally defined because they each correspond to an atom. And so the entire generation is also local and scalable and extensive, allowing to construct molecules of arbitrary size. So this might be a good way, if you want to generate large graphs, then generate features for that graph and a general data distribution of graphs to give you local features representing a node and its surrounding neighborhood, given some physical intuition that the node is only interacting with its local neighbors. So once you've got those local features, then you can use those features to construct graphs of arbitrary size, which is a neat idea. And like without this, how do you scale graph machine learning? It's like really difficult to perform summations over all combinations of different n-body orders interactions. So the score model can be controlled without retraining by simply substituting a new reference set of local atomic environments for the similarity kernel. So they're actually just going to do the zero shot. Once they've got these features from the pre-trained network, they're going to put them into something that mimics diffusion, which is not quite diffusion, but it mimics diffusion, and then show how to choose a context set of these local features to generate structures which fit into a point cloud prior, which might be the trajectory of the atoms across two fragments of molecules, like that diagram that we saw here. So we're going to make a point cloud across, bridging the gap between these two, and that allows for good design of different molecules. And so that's clearly the application that they have in mind when doing this method of a similarity kernel. So looking at this again, I think one important thing to note is that high energy, we've got a negative sign here inside exponential. So high energy means low probability. Low energy means high probability. So we want low energy, high probability, interesting molecules. And they're going to train a score network involving this positional force and alchemical force for the chemical composition, and compare this diffusion model to another model. So this is the diffusion energy E, and this is some simple linear interpolation between the restoring potential, which is this quadratic, as Arvid was talking about, and this quantum mechanical physical potential. So we're saying this similarly as the same as this quantum mechanical potential, only samples from a global Boltzmann distribution and finds very stable molecules such as water and carbon. But it's slightly better because of this restoring potential, which is guiding it away from somewhere uninteresting. And we're going to study how the learned diffusion model, which is always going to point towards a data set. So if your data set contains millions of molecules, which are large, is going to point towards those molecules. So what's the difference between pointing towards this data set of large molecules and pointing towards the molecules which are fragmented? So they're going to study that. The time intervals where the learned energy differs most from this linear baseline are the most critical. In these regions, the diffusion model has learned to guide the generation towards chemical space, more similar to the training data, rather than towards the modes in the Boltzmann distribution. The learned energy depends on two variables, and they're going to probe the behavior by constructing a distance between ground truth and the generated molecule at time t, which is this noisy molecule. And this distance is the standard deviation of atomic distances between the ground truth and the positions of the current molecule xt. And so that's some like distance between the ground truth and a generated molecule through time. That's going to be used in these plots right here. So you've got this distance on this axis, and you've got diffusion time on this axis. So in diffusion, we're going to start from the restoring potential, quadratic potential is going to be high energy, and we're going to progressively diffuse, reducing the time to 0. So we're going in reverse, not noising, we're denoising, and cooling this diffusion distribution down. And then plotting that against the distance to a benzene molecule, which is the ground truth x naught, across different distances, you can see that this is a smoothly varying potential energy. So then it's going to guide away from, it's going to guide towards sort of global minima in a smooth way. And then looking at, yeah.
Well, I was wondering, is there, so we have on one side, we have, you could argue, some very physical thing because we define the quantum mechanical force. On the other side, we also have something that looks a little bit like a high temperature case, right? We just heat everything up and it sort of floats more or less freely. Do you think there is some physicality to the steps in between, to these denoised or semi-denoised representation, and whether they are like say you take a molecule, you add up heating it a little bit, and you would sort of expect it more likely than not to be in one of these intermediate steps, perhaps.
I'm not sure about that.
Mm.
I don't know.
Because you could think that might open up some really interesting features, right? Like how do you combine two molecules into something new, right? Like synthesis. What is like a good path going from different states to others, and if you know, say you know certain, because it's all local, right? So you know it's all supposed to work on the local environments. And if you know which local environments tend to work well because you have a catalyst in place, you might be able to find out what kind of catalyst works potentially for turning molecule A to molecule B, because in this diffusive space, that might be the shortest path between them. But again, that is highly speculative.
Yeah, it's like if you were to trying to design new molecule, how do you actually make them? Like
Yeah,
maybe
exactly.
this to tell you, like, how do you make them as well,
Yeah,
as looking at the finished product.
and because it seems to have like some sort of idea about the quantum mechanical forces, so it might find by this denoising like what is like a convenient way to go about in this highly dimensional space.
Mhm.
Yeah.
So the landscape depicts the learned energy of benzene molecule at different combinations of deformation level on this axis, the y-axis, and time, the x-axis. The colored lines on the diagonal show how the energy and deformation level changes for the real generation trajectories for the diffusion model. So we're starting with the point clouds, and because we've got this atomic switching going on, they're not actually going to land in benzene molecules necessarily, but these are trajectories of generation for this diffusion model that's going to generate valid molecules. And they are a very similar change in color as this underlying deformation time plot. So the energy is a function of time, and deformation from the final molecule are similar for all generated molecules and closely mimic the landscape drawn here for benzene. So this, while the background is benzene, the lines, they're not necessarily benzene, but you can say the colors change quite in a smooth way, similar to the background. So it's going to mimic the landscape, this potential landscape, which is smooth. So, okay, the potentials are smoothly straight lines, going in straight lines in this space, really efficient, going from global minima to high probability, low energy local minima, which represent interesting molecules that lie in the data set. That's great. So how do we learn from this? Energy profiles of diffusion trajectories. Across 10 examples, the learned energy smoothly decreases during generation, even when the atoms overlap. In contrast, this baseline, the E linear, so it's not the diffusion, this is a baseline, evaluated on the same trajectories, has a much rougher profile. So whilst we're going smoothly, progressively finding local minima, here we're bouncing between local minima all over the place. It's like fairly ill conditions. This is well conditioned. So algorithmically efficient diffusion versus algorithmically inefficient basic annealing schedule, which finds rubbish molecules, whereas the algorithmically efficient diffusion model finds great molecules. So the gray line shows energy along ODE trajectory. Okay. The baseline method, so the E linear, using just quantum mechanical force fields, generate fragmented molecules. So that's a relaxation of uninteresting point cloud soup states, relaxation to make physical. So you're just going to get carbon atoms clumping together. You're going to get oxygen atoms clumping together. You're going to get hydrogen atoms clumping to oxygen atom. It's like the closest way to get to a local minima, because it's quite a rough energy landscape. So you can't jump between local minima, whereas this diffusion is going to make the energy landscape smoother. So you're going to be able to smoothly guide towards like a global minima. And it's not that you're jumping between local minima, but there is no local minima at first, and then you're progressively finding some local minima. The linear one barely does better than the physical quantum mechanical potential by somehow annealing it, and that's why this linear potential decreases in quite a jagged way. Yeah, you get bigger molecules, but they're still not the most interesting ones. They're still fragmented. They're larger, but they're high energy molecules, so they're low probability. And diffusion models penalize fragmentation. So this is really the key plot here. So this is the insight that they have gained from diffusion models. Takeaway points. The plot is showing in increasing time through the diffusion simulation from left to right, so denoising. It shows two different energies and compares their properties and is interpreted via relaxation potentials of two annealing schemes. Okay, so what are the two annealing schemes? And linear, which is the slightly less bad one, and quantum mechanical, which is the purely physical but finds local minima immediately one. And comparing these two trajectories, so each line is a trajectory of this annealing process, and we're going to compare the measured quantum mechanical physical energy to the Lorentz diffusion energy. Okay, so why for the quantum mechanical trajectory would the quantum mechanical energy immediately start decreasing? Because that's what's being optimized when you're doing this trajectory. Why for the linear trajectory does the quantum mechanical energy start increasing? Because the potential is dominated by this restorative term. So this restorative term is going to push you away from clumping together to carbon dioxide, water, and dinitride molecules. So that's what that's useful for. We're going to immediately go away from the physical to bring us towards some better minimum, which is like but then we never quite reach our physical configuration. So we're going to have high energy, low probability particles if we use this linear trajectory. Now, let's look at the Lorentz diffusion energy, which is going to always point towards the data distribution. So which one is closest towards the data distribution? The one with the lower energy, because it's high probability under the data. So quantum mechanical trajectory has high energy, low probability under the data distribution, because you don't see any fragmented molecules in the data set. Whereas for the linear trajectory, they're more clumped together, larger molecules. They're closer to these noise molecules that you find in the data set. So this is to show that there is a gap between fragmented molecules orange and clumped together molecules blue. And this gap is a penalty which is useful for generating molecules that are close to the data distribution. It's going to defavor fragmentation. And that's the insight. So one question I had here is that, okay, if they're generating molecules that are close to the data set and the data set has only physical molecules in, so these are molecules that exist and a high probability, then why is the diffusion energy so high for the quantum mechanical trajectory at the end? And there's a number of reasons for this. Well, because the quantum mechanical trajectories produce physical molecules. Yes, they are physical, but no, they're not in the data set. So this large data set that's used to train this diffusion model, it doesn't contain any basic molecules, or contains very few relative to the larger, more interesting molecules. So it's going to give them a high ill-behaved, unbehaved density, because you're not really when you're doing diffusion, you're not really learning their density on the support of the valid molecules. You're learning to point towards the valid molecules. So where you haven't got much data, which is like, for example, these smaller molecules which are not interesting and not in the data set, then you haven't learned the diffusion score or energy very well. And so it's not going to be very well behaved. And so that's quite expected. So even though these are physical molecules, they have not been learned by the diffusion model. And that's okay, because maybe you don't care about them. So a diffusion model seems like a good thing to do if you have a data set and you want to generate things that look like the data set. But it's, in terms of generalizing outside of that data set to emulating a quantum mechanical energy, is going to be very different. It's definitely not going to be the same as a quantum mechanical energy. So it's not going to kind of generalize outside of that data set. But that's fine, as long as it can point towards like the distribution, the support of the distribution of interesting molecules, then you can still generate interesting new molecules. So general in that sense. Okay, so
Ben, just so you know, I think we're gonna have to stop at 1:35. We'll go 5 minutes
sure.
over, but yeah.
So those are the lessons that have been learned from this. But there's some problems with diffusion, lack of scalability, because they're global. Perhaps they're global molecules. They're global models that depend on every atom and are not local, so not message passing. In this case, I think they have defined them as being message passing. It's limited control, so that controlling diffusion models requires specialized training. And finally, low transferability. The problem is training for a specific problem that you want to solve, like simulating particular proteins, needs large amounts of data for the part of the distribution one is targeting. For example, if I want to sample from sol-based amino acids, I would have to train a diffusion model specialized to those molecules, and that might not be enough data for the more specialized. And as the more specialized your problem becomes. However, interpolating between an analytical restorative potential and a physical potential remains a sound idea. So building on that insight, they're going to take the features learned from this parameterization of their neural network, which is a message passing one, and then use them within similarity kernels. And so I'm going to skip the similarity kernel bit because it's quite problem specific, but it is a very simple method of guiding towards graphs, molecules that you're interested in guiding towards without doing any further training. So it's very fast as well. But it only works because of the parameterization of this model. So as a final point, I just want to cover the message passing algorithm. So the takeaway points of this parameterization is that it's an efficient and systematic functional form for molecular problems, and it's efficient because it's taking a tensor product across atoms rather than edges, yet it's still increasing the body order, the number of interactions between atoms. And message passing provides a sparsification of this full basis, where basis means you can construct any function, and does not depend on the positional correlation of far apart atoms. But you can still represent all physical potential functions with this basis because it's a full basis. And how do they construct this? You've got feeding a set of features from circularly symmetric functions, which don't depend on angle, but just distance. So this is a scalar distance. And that gives you sort of radial functions, and it becomes a full basis by crossing it with angular functions, which is the spherical harmonics. And they form representations of the group rotations. So together with this R, form a complete basis of potential functions that have the right physical invariances. You can immediately see its translation invariant because it depends on the relative position. So it's only the edges that are input, and the edges, once you translate that edge, it doesn't change, this Rij, because it's between atom I and atom J. So translation invariant, but also rotationally equivariant because of these spherical harmonic functions. So final point, really clever bit, how do you get n-body interactions without n layers of a message passing neural network, which is hard to scale and comes with its own problems of over smoothing. Well, you sum complete basis at a parent node, and the sum is only over the neighborhood size, which only has constant scaling in the molecule size. And the computationally expensive sums and over triplets for 3-order problems are absorbed into this term, which has constant computational cost with respect to molecular size. And then this tensor product, which is only a partial tensor product, it only takes tensor product across the channels L and M. Okay, and hence, and not across this K channel, because this K channel has been summed away. But still it's going to have inside it all of the third order interactions, because in taking a sum over edges and then doing a tensor product over different channels, you get all the cross terms of the edges, which is going to give you in turn these third order, fourth order interactions depending on the order of mu here. So mu is the order of the number of atoms in the interaction. And that's a really clever idea, and it might be transferable to other graph methods if you want to scale graph methods. So I think that's what I'll finish with. And thank you for listening and for the discussion as well.
Thanks, Ben. Yeah, I'm sure we want to scale graph methods. So maybe you can write the paper about how to transfer this to like a generalized problem.
We'll see.
Yeah, thanks for presenting, and thanks everyone for coming, and have a good weekend. And next week we don't have paper club, just so you guys know, but we'll be back on in 2 weeks. See ya.
Thank you, Ben. Thank you, everyone. Great paper.